So these notes are about binomial random variables. And a binomial distribution has its own set of conditions. And for you to remember that, I'm going to give you an acronym. And that acronym is BINS, B-I-N-S. So we've seen conditions before for like a normal distribution or a t-distribution. The conditions for a binomial distribution are a little bit different. You probably won't be able to guess any of these letters except for the I at this point. So the I stands for probably what you think it stands for. Let's start with the B though. The B actually stands for binary. So binary means two choices. And in the case of a binomial distribution, we view those two options as being one is either a success or a failure. So that's the first condition. The second condition, we want to make sure things are independent. So that's the one you probably already knew. The N most definitely does not stand for normal. The N stands for number of trials being fixed. So N, we need to know that there's a fixed number of trials. And then S stands for same probability for each one of those trials. So same probability of success for every trial. So the N means we know the exact number of trials, and the S just makes sure that the same probability of success holds for each of those trials. And then going back to the I for just a moment, when we're talking about trials, we know for the independence condition we use the 10% condition when we're sampling without replacement, or if we're doing an experiment or we have trials happening, we just know that the result of one trial doesn't give us any further info about the other trials, so therefore the trials are independent. So to use a binomial setting, we got to meet these conditions, and it follows this BINS acronym. The second part here says, what is a binomial random variable? What are the possible values of a binomial random variable? Okay, so in general, a binomial random variable is a scenario with multiple trials, and we're interested in counting the number of successes. So if we're counting things, this is definitely a discrete random variable. So an example of a binomial random variable that we've looked at would be flip a coin 10 times and count the number of heads. Like a heads would be a success. So that's an example of a binomial random variable, which you could classify as being a discrete random variable because we count the number of successes. So what are the parameters of a binomial distribution? And let me remind you, when we talk about a normal distribution or a normal random variable, call it x, we use this notation. X is following a normal distribution. The parameters would just be the mean and the standard deviation. We learned that a long time ago. So for a normal random variable like x, we could say it's normal, and we know its mean, we know its standard deviation. Those are our two parameters. For a binomial distribution, let's say we have this random variable x. Here's the notation you can use. X follows a binomial distribution, that little squiggly line. And the two parameters aren't mu and sigma like they were over here. They are n and p. And those two are actually pretty easy. N is just the number of trials, so that's why we have to have a fixed number of trials, like we talked about, that condition. And then p just tells us the probability of success. Okay, so what's the most common mistake students make on binomial distribution questions? And that mistake is that they fail to realize or identify that the question's talking about a binomial distribution. So they'll try to use a normal distribution or a t-distribution, and it's totally out of place. So you've got to be able to realize or identify when a binomial distribution is appropriate. And in doing that, you can use the BINS acronym to see if it meets those conditions. So we're going to start off with an easy example here. It says Bill makes 80% of his free throws. Pretty good free throw shooter. He shoots 5 free throws, and we will assume each shot is independent. Let x equal the number of free throws made. So x is definitely a random variable. And we're going to start off by verifying that x follows a binomial distribution. So when it says verify that this is a binomial setting, we need to speak to each one of these conditions. So let's start with BINS. So the B stands for binary, meaning there's only two choices. So we need to identify what would a success be and what would a failure be. Well, we're talking about free throws in this case, so apparently a success would be a made free throw, and a failure would be a missed free throw. So the B's good, and then the I, how about independence between free throws? Well, it says in the problem, we're going to assume that each shot is independent. So to meet this condition, we can just say given in the problem. And then for the N, that definitely doesn't mean normal here, right? Binomial distributions are not normal. The N stands for a fixed number of trials. And in this case, it says he's going to take 5 shots. So 5 would be the number of trials. That's fixed. So the N condition from Ben's is good. And then the S stands for the same probability of success each time he shoots it. Well, if he's an 80% free throw shooter, that means the probability of success in this case is 0.8 for each free throw. So we're good on the Ben's condition. That means we can say that X, our random variable, follows a binomial distribution with 5 as the N, the number of successes, and 0.8 as P, the probability of success, which also goes right here. 5 is our N, P is 0.8. Now, what the heck is K? Well, if you use your calculator or if you use the formula on the formula sheet for a binomial random variable, K is sort of this exact outcome, and it tells us the number of successes, or in this case, the number of makes that are desired. For example, if I ask you what's the probability that Bill makes exactly 3 free throws, K would be 3. But more on that in just a second. So part C says using the Binomial Pdf, right, Binomial Pdf command in your calculator, make a table for the PDF of the random variable X. So where is that command actually? Well, you remember normal CDF? It's in the same place. So if you hit second vars, which is the distribution button, you'll find Binomial Pdf in there. And then your calculator will ask you for a few specific things. It'll ask you for N, the number of trials, P, the probability of success, and then K, what's the exact outcome that you want? Or it'll call this actually the exact X value that you want. So that's the X value desired. And we'll go through each one of those when we make this table. So to start out on the top row, this is our X right here. So the top row is all the possible outcomes for X. And remember, he's shooting 5 free throws, so he could make 0 out of 5. He could make 1, could make 2, all the way up to 5 free throws. And then the row below that, let's give the probability for each one of these events. So if we use the Binomial Pdf command, 5 is the N, P is 0.8, and in this case, for 0, we put 0 for the X value desired, and we get 0.0032. If we put 1, we get 0.0064. For 2, 0.0512. For 3, it's 0.2048. For 4, 0.4096. And for 5, 0.32768. Now, I haven't checked this, but if you add all these up, they better add to 1. Also, I hope that it makes sense to you that 4 had the highest probability. I mean, at the end of the day, Bill's an 80% free throw shooter, and making 4 out of 5 would be 80%. So 4 was his highest category. His lowest was going 0 for 5. Okay, so the other calculator command we have to talk about is the Binomial Cdf command. And the C actually stands for cumulative. When you think of cumulative, you can think of things accumulating or growing. So the Binomial Cdf command actually calculates the sum of all those probabilities up to a certain point. So if I tell it to add everything up to 3, it would sum all these probabilities up for me. So whatever value you pick for K, like what's the probability Bill makes less than or equal to K shots, it's going to add up all those probabilities up to whatever number you set for K. So the PDF command that we talked about up here, that finds specific values. So it finds single probabilities like the ones we put in this table. The CDF command, again the C stands for cumulative, it accumulates over multiple probabilities. For example, in part E it says, use this to find the probability that Bill makes 3 shots or fewer. So probability X is less than or equal to 3, which is probability hits 0, 1, 2, or 3. So we could add up all of those individual shots, or we could just use Binomial Cdf in our calculator and tell it to go all the way to 3 for that X value. So definitely more efficient here to use Binomial Cdf, and it adds up automatically all those probabilities up to and including 3 and gives us 0.26272 as our answer. Okay, so the next part of these notes talks about the binomial coefficient and the formula for a binomial probability. So the binomial coefficient you'll be familiar with if you've ever done permutations or combinations and figured out how many different ways we can arrange things or group things in math class. So if you see something written like this in tall skinny parentheses with a number on top of another number, that means n choose k. In the formula, you won't have to know this, but the formula would be n factorial over k factorial times n minus k factorial. So if you're really interested in using this command, the n choose k, you go to math, PRB, and then it's NCR. So in this case it would be n choose R. So I wanted to illustrate that for you here, but I'm not going to ask that you know it, and you don't need to know it in particular for the AP exam. The formula, though, for the binomial probability, this is the one that's actually on the formula sheet. So if I asked you, what's the probability that Bill makes exactly k shots? So the probability of getting k successes. And again, this is the one that's actually on the formula sheet. It starts out with n choose k, the binomial coefficient, times p to the k. Remember, p is the probability of success, k is the number of successes, multiplied by 1 minus p, which would be like a failure, right? If p is a success, 1 minus p would be a failure, to the power of n minus k. And this is the one that's actually on the AP formula sheet. And this formula is actually a lot more intuitive than it looks. We'll go through here with a couple examples to illustrate that. Part F says, what is the probability Bill makes only 1 shot? And provide the proper equation. This is going to be important because sometimes, especially multiple choice questions, they feature this notation, so I want you to be comfortable with that. So what's the probability Bill makes only 1 shot? Well, let's start off with, he's going to take 5 shots. So maybe it's the first one that he makes, and the rest of them he misses. So it's 0.8 times 0.2 times 0.2 and so on. But obviously that's not the only way, right? What about a scenario where let's put down the 5 shots again. He misses the first shot, but makes the second shot, and then misses the other 3. Remember, Bill's an 80% free throw shooter, so my purple 0.8 here, that represents the make, that's the success, and the 0.2s, those are the failures. So he could make the first shot and miss all the others. He could make the second shot and miss all the others. He could make the third shot or the fourth shot, or how about we skip a few all the way down to the last case where he misses the first 4 and makes his final shot. So in this scenario, there's 5 total ways that he could just make the 1 shot and miss all the others. So that comes from this idea of take 5 shots and have 1 success. So for each one of these scenarios, we have 0.8 and then times 0.2 times 0.2 times, or there's only 1 success and then there's 4 failures. So we'd have 0.2 to the power of 4. And that's the same for this as well. We still have a 0.8 in there times 0.2, 0.2. So 1 success and then 4 failures, which is also the same for the last one. You have 1 success and 4 failures. And since we have 5 different ways for this to occur, if we add all these up, we'd have 5 times this 0.8, like 1 success and 4 failures. Or if we had it written the way the formula writes it, it would be 5, choose 1, right? 5 total trials, choose 1 success, and then 0.8 to the power of 1, that's our 1 success, and then 0.2 to the power of 4, because that leaves us with 4 failures, which our answer is 0.0064. Shouldn't be surprised because that's also the answer from the table. We just wanted to feature the equation that you might see on a multiple choice question. Okay, part G says, what's the probability that Bill makes 4 shots? And provide the proper equation there. So the probability that X is equal to 4 in this case, because X is the number of shots Bill makes. So let's start it the same way. It says Bill makes 4 shots, which means he must miss one of them out of the 5 shots. So maybe the first scenario is, out of the 5 shots, he misses the first one, and then the last 4 are successes. Or out of the 5 shots, maybe he misses the second one, but he makes all the other ones. And we could continue this pattern all the way down to he makes all of them except the last one. So I know this is a little bit of a simplified example, but if we use the formula, it's he has 5 shots and he has to make 4. So 5 total scenarios, 5 total trials. We're going to choose 4 successes. And then each one of these, we have 0.8, that's a success, 4 times. So it would be 0.8 to the 4, and then 1 failure, so 0.2 to the 1. Which simplifies to 5 times 0.8 to the 4 times 0.2, which is 0.04, or 0.4096, excuse me. So the binomial coefficient just tells us how many different combinations there are. In this case, there was 5, just like in this case, there were 5 as well. And then we do success probability to the power of however many successes there are, and then the failure probability to whatever's left over, how many failures there are. Part H says, what's the probability Bill makes 2 or 3 shots? So we have 2 different scenarios to consider. Probability that X equals 2 plus the probability that X equals 3. Now, I know we could go right to the table and get those right now, but we're going to illustrate these with the equation. This is the last one we're going to do. So for 2 successes, let's start out with 5, choose 2, because there's 5 total shots. We're going to choose 2 successes, and then 0.8 to the power of 2, right, because we have 2 successes, and then left over would be the other 3 considered as failures, so 0.2 to the 3. So that represents 2 successes. And then how about 3 made shots? So we could start out with 5, choose 3, and then 3 successes, so 0.8 to the 3, and then 2 failures, so 0.2 to the power of 2, which is 0.0512 plus 0.2048 for a grand total of 0.256. Okay, and then without using the actual equation from the formula sheet, part I asks, what is the probability that Bill makes no more than 4 shots? So the notation for that would be X is less than or equal to 4. So you can't go above 4, but you could make 4. Another way to write that, which would be totally equivalent because this is a discrete random variable, would be what's the probability that X is strictly less than 5 shots? So that doesn't include 5. In fact, that just includes everything below 5. So the probability of 0 plus 1 all the way up to 4. So if we went that route, where we add up all those cases from 0 to 4, we would use Binomial Cdf in the calculator. Or we might go the other way and say, well, if there's only one case not included in this, we might just say, well, that's just the same as 1 minus the 5 case. So if we do 1 minus just that individual probability X equals 5, that would be Binomial Pdf. So that route would be 1 minus 0.32768 if we use Binomial Pdf, which gives us 0.67232. So that's the probability that Bill makes no more than 4 shots. So either way you want to go, you want to use Binomial Cdf, that works well. If you want to do 1 minus this individual case, you could just do PDF for the 5 case. You should get this answer regardless. And then part J says, what is the probability that Bill makes at least 3 shots? So the probability that X is greater than or equal to 3. Well, that's the same as saying the probability that X is greater than 2, right? If I'm including everything 3 and above, then that's the same as X is greater than 2. So if I want to feature all the stuff bigger than 2, I could just do 1 minus all the stuff that's 2 or lower. And the reason I do that is because I can use the Binomial Cdf command for that part. So the Binomial Cdf command starts from 0 and it reads up to this boundary. So if I have less than or equal to 2, I would do Binomial Cdf, n is 5, p is 0.8, and then the x value I'm interested in would be 2. So that's the same as 1 minus 0.05792, and I got that number from the Binomial Cdf command. So our answer is 0.94208. That's the probability that Bill makes at least 3 shots. Now, could you have just looked at the table and added those up easily? Yeah, of course. I just wanted to show you a few different ways that you might use Binomial Cdf or Binomial Pdf. Okay, so the last page here talks about the mean and standard deviation for a binomial random variable. We can say if a count x has the binomial distribution, the number of observations is little n, and the probability of success is little p, what are the mean and standard deviation of x? Well, let's start with, we know x is following a binomial distribution with n and p as its parameters. I hope you like my color coding. The mean of x, and this is actually on the formula sheet as well, the mean is just n times p, the number of observations times the probability of success. The standard deviation of x would just be the square root of n times p times 1 minus p. And both of these guys are actually on the AP formula sheet. The final example here, the makers of a Diet Cola claim that its taste is indistinguishable from the full calorie version of the same cola. To investigate, an AP statistics class prepared small samples of each type of soda in identical cups. Then the teacher had volunteers taste each cola in a random order and try to identify which was the Diet Cola and which was the regular cola. Overall, 23 of the 30 subjects made the correct identification. If we assume that the volunteers really could not tell the difference, then each one was guessing with a 0.5 chance of being correct. Let x equal the number of volunteers who correctly identified the colas. Part A says, why is x a binomial random variable? And we need to go right to the BINS acronym to meet each one of these conditions to show that. So for the binary one, for B, well, we know we have a success and a failure option. The success would be a correct guess, and then a failure would be an incorrect guess. And then as far as I is concerned, I can't use the 10% condition, but since these were subjects in an experiment, it's safe to assume that their guesses are independent. And then N stands for a fixed number of trials, and in this case, we have 30 people each accounting for a trial, so the number of trials would be 30. And apparently, we're assuming that the chance of them getting the correct guess is 0.5, right? We're given that in the problem. So the same probability of success applies for each person here, which is 0.5. Okay, so the BINS condition is good. So we've shown that x is a binomial random variable. Part B says, what's the mean and standard deviation of x? Interpret each value in context. So let's start with the mean. And the mean's actually pretty simple. We just take n, the number of trials, and multiply it by p, the number of successes. So 30 times 0.5, we'd expect 15 correct guesses. Let's give an interpretation of that. So we could say in the long run, or if the experiment were repeated many times with subjects randomly guessing, the average number or the expected number of correct guesses would be about 15. Okay, how about the standard deviation? And again, this formula is on the formula sheet. It's the square root of n times p times 1 minus p. So N is 30, P is 0.5, and then 1 minus 0.5 would be 0.5 again, which gives us 2.74 correct guesses for our standard deviation. And then hopefully you recognize this type of interpretation. We could say we'll typically be off from the mean by about 2.74 correct guesses if we did this over and over again. So the number of correct guesses would typically vary by about 2.74 from the mean of 15 in repeated random experiments. Okay, and then lastly here, part C. It says, of the 30 volunteers, 23 made correct identifications. Does this give convincing evidence that the volunteers can taste the difference between the diet and regular colas? Okay, and in your experience, when a question asks, does this give convincing evidence, that typically means a hypothesis test is involved, and certainly a p-value or a probability value is involved. So in this case, what's the probability of us getting at least 23 correct guesses if there truly is no difference? Well, we just went through all that trouble of proving that this thing was a binomial random variable, so now we should be able to calculate this. In fact, I'd like to use the Binomial Cdf command. I just need this to say x is less than a number. So if you want to know what's the probability x is something 23 or above, that's 1 minus the probability that x is 22 or below. And the reason I do that is because now I can use that Binomial Cdf command. It will only give you the probabilities below a certain upper bound. So we'll use Binomial Cdf. Our n is 30, our p is 0.5, and the x value we're going to go up to is 22. So that gives us 0.9974 to subtract from 1 for an answer of 0.0026. And we need to interpret that here. What does that mean? Well, if that's our p-value, that's definitely convincing evidence, right? So we could say we do have convincing evidence that the volunteers can taste the difference. In fact, 23 is way more than 15, right? So that p-value is so small. So we could say, since there's such a small probability of getting 23 or more, I just write 23 plus, of getting 23 or more correct guesses if they somehow couldn't tell the difference and were just randomly guessing. So that small p-value is definitely convincing evidence. If you're assuming that they don't know the difference at all, it'd be really rare to get 23 or more correct guesses. All right, so that concludes your introduction to binomial random variables. That's all for these notes. I'll see you in class.